As we've mentioned, both TC and the other chemical PC, perchloroethane, are two of the most prevalent contaminants that we have at our sites, at our hazardous waste sites. And so this new exposure or newish exposure pathway is one that we refer to as vapor intrusion. So it's the vapor intrusion pathway is the migration of these volatile chemicals such as TC and PCE in the subsurface, so it could be in the soil or in the groundwater, and it's migration upwards through the soil and soil gas, and its ability to potentially enter into the overlying buildings through cracks and conduits and so forth. The physics of the vapor intrusion pathway is very similar to what you may be familiar with, not so much here in this area, but the radon gas intrusion that we see a lot back east. And so we've learned a lot from just what we know from radon and assessing the pathway that way. But this is relatively new exposure pathway that we're faced with these, again, these large contaminated groundwater sites with, in this area particularly, with shallow groundwater contamination or just shallow contamination. Go this way. So here's a schematic or cartoon of the vapor intrusion pathway. Let's see if I can do this. So if we have contamination here in the subsurface, it could be groundwater. So it volatilizes and then migrates. It's not a straight little path, but it migrates through the subsurface, soil gas, and potentially enters into the different types of foundations. Here it's showing residences with the different types of foundation, a basement, a crawl space, or a concrete slab foundation. So there's the potential for this, and then also into non-residential commercial buildings as well. So here's just another type of cartoon that we've used. It just shows that, so most of the information to date that we've been gathering is on groundwater and soil. We know what's in the groundwater. We know that the chemicals that we're seeing in the groundwater, again, TC and PC, can volatilize upwards. And this is how it can enter into the overlying buildings. So this is the pathway where EPA had to take another look at all our sites. So what we did in both our Superfund and RCRA programs, we assessed over 200 of our TC and PC sites and prioritized them as far as this potential subsurface vapor intrusion pathway. And at the higher priority sites, a number of them which are in Silicon Valley, we took another look and did a vapor intrusion investigation, a more comprehensive vapor intrusion investigation. So some of the criteria we're looking at, and again, as it pertains to the Silicon Valley sites, it's just simply the depth to contamination, this depth to groundwater. It's shallow here, anywhere from 5 feet to 20 feet below ground surface. We have high concentrations at a number of our sites with TC, PC, and there's other volatile organics, as some of you have mentioned. And so we see it in the soil gas, and the groundwater. And what else we're looking at is what's the use, the current land use of it. What kind of land use is overlying this contamination? Are there occupied buildings? Is it an area where we expect future occupancy or future development? And then also we use our professional judgment. We have a lot of experts that are working on this issue, and part of EPA's program is active community involvement. So we go out to communities, we explain the potential issue, and get their input and feedback on both the assessment of these sites and contamination. So here is a little bit different picture. It shows some of our sites in Mountain View. This is the MEW site, and it shows the extent of that groundwater contamination. And what you're seeing in this pinkish area is what EPA actually referred to as the vapor intrusion study area. So what EPA did is we took a closer look of all the buildings or the overlying that groundwater contamination. As you can see from that area, it was well over 100 residences, probably over 120 commercial buildings where EPA did an assessment. And ultimately in 2010, we did select a remedy to how to assess and remedy the situation in case we did see a vapor intrusion problem. And then in nearby areas, there's just other sites within Mountain View as well as the South Bay where we're looking at the issue. So what Kathy's going to talk about is some of the sampling and investigation tools that we have when we evaluate for vapor intrusion, and then subsequently how we can mitigate for vapor intrusion.
Yeah, you're doing mitigation. Yeah, okay. Okay, so where do we collect samples? Well, let me talk about, I brought some show and tell items, but let's just talk briefly about where we would sample for air. So we have, you can see indoor, the breathing zone, typically, coffee table height, toddler height, that's typically what we're looking at. We'll sample the subslab, soil gas. I like that ringtone. Subslab, soil gas, outdoor air, of course, because particularly for some of these contaminants, the outdoor air can be pretty high in it. So benzene would be an example. We get that from gas stations. Every car has gasoline in it, has benzene. So the outdoor air, particularly in urban areas, is going to have relatively high levels of benzene. So for any of these contaminants, we want to know what the outdoor background level is. So we'll sample the outdoor, the indoor, the crawl space, if it's relevant, a basement if need be. We don't do so much basement sampling here. Not that many houses in our area have basements. And of course, we have our groundwater samples and soil gas samples. So what are some of the tools that we use? This is an example of shallow soil gas sampling. So you can see this guy is just drilling right through the slab, and it's just a fairly narrow drill. These probes are pretty small. And then here's a sampling device that's hooked up to a soil gas probe. So with the soil gas, this is not actually a soil gas probe. This is a subslab probe. And you can see it's basically just a metal tube, just hollow. And so the hole that we would drill in the slab is basically about that big. And then this gets dropped in, and then we grout it up so it's nice and tight so that when we're taking a sample of the subslab soil gas, we make sure that we're taking it, the air sample is coming from here. It's not coming up through the conduit, through the pathway here. And so that's just a soil gas probe. I don't know if you guys want to pass these around or not. Anybody care? You can come up later and see these. This is our standard air sampling canister. This is a 6-liter Suma canister. Suma is a trade name, but it's basically a stainless steel evacuated canister. So this is hollow inside, and the reason that it's sort of basketball shaped like this is that it's nicely polished on the inside. And so you want it to be spherical, so when the air sample is in there, it doesn't get trapped in the corners. If this were a square box, it wouldn't be nice and homogeneous. So this is a kind of a standard shape for Suma canisters. And so the way we get this from the lab. It's negatively pressurized at the lab. Well, first they clean it. It's got to have absolutely no contamination in it. So they clean it, they bake it out, and then they negatively pressurize it at the lab. So it comes to us at about minus 30 psi. Then we'll attach one of these flow controllers, and the flow controllers are set so that once we open the valve, it will actually draw in air over whatever time frame that we specify. So if we're sampling in commercial or industrial areas, we'll typically sample over a typical workday. It might be an 8 or 10-hour workday. For residential sampling, we'll typically set the flow controller so it fills over 24 hours. So we'll meet with the residents, we'll set this up basically on a coffee table, go ahead and start it running, and then we come back just about 24 hours later and pick it up. And so then we send it to the lab, and what they have is a whole air sample. So that's all you have in here, because it's been filling over 8, 10, 24 hours, whatever it is. It's a sample of the air from that residence. And so the analyst will take it, and they will take basically a small aliquot of the air that's in the canister, and then they run it through the GCMS, the gas chromatograph mass spectrometer. And then that shoots out the information at the far end, sort of like CSI, but not really that fast. And it tells you what the contaminants are in the air. So that's kind of a standard way that we do air sampling. A more recent method that's starting to come into play, and it was actually the focus of a big research project that Alana and I worked on, is a sorbent-based sampler. And so this one you can see is quite a bit smaller. It has this basically diffusive membrane here on the outside, which basically just prevents the turbulence or the air being sucked into the device too quickly. This is completely passive. The inside of this is just carbon. That's all it is. And so the carbon within this sampler, and we've taken this thing in and out so many times I can't even get it out anymore. Anyway, it's carbon that's in a steel mesh tube. And so it sits here, and we'll set this out in a home for anywhere from 3 up to about 14 days, depending on the site and the contaminant that we're looking at. And it just passively sorbs the contaminants. So the carbon that's in here has a known uptake rate. And it's different for each contaminant, but it's that, what's called the Q value, is established by the manufacturer. And so when the laboratory gets this, they will desorb, or in some cases chemically extract, the contaminants that are on that carbon sorbent, and then they'll measure what's there and then use the Q value to figure out what the equivalent air concentration is. So the research study that Alana and I and a couple of other coworkers worked on was to really see if these were as good as the SUMA canisters. And we pretty much found that they were. So we're seeing this as a potential new technology that we might see more use of in vapor intrusion studies. Okay, so this is just, again, the different places where we would collect samples. The thing that's a little bit different about this is for commercial buildings. So in addition to having indoor and outdoor samples, we'll also take a sample up by the HVAC system. So we will take an air sample basically right where the air intake is on the roof for the air conditioning system. And then in a lot of commercial buildings, they may have equipment rooms where they have direct access to the subsurface. And so these kinds of conduits or things that are actually cut through the slab, these can be utility conduits and things like that. That might be a place where we're taking what we call a pathway sample, and we typically find higher VOC concentrations there. Okay, this is an example of a subslab soil gas sample. This is a smaller version of a SUMA canister. This one is actually only about 300 milliliters, so there's nothing for scale there, but it's basically like fist-sized. And so we call this a grab sample. On this one, we open the valve, and it basically fills over about 3 minutes or so. With the indoor air sample, we leave that out typically for 24 hours. With the soil gas sample, it's a grab sample, so it's basically just a one-time sample. Now, you can see from this photo, one of the things that makes subslab sampling so problematic, and particularly here in California, this is somebody's carpet, and we have cut into it and drilled a hole through their slab. How many people want a hole drilled through their slab? Not very many of you. So where we end up doing these, typically in California, might be in a garage, it might be in a closet. People are very unwilling to let us drill through their hardwood floors, rip up their carpet, things like that. So we've been proponents of doing more indoor air sampling and then doing the subslab sampling if the indoor air concentration suggests that there may be a vapor intrusion problem. And so we track it down from the inside out instead of the outside in. This particular site was actually unused multifamily housing. So it was multifamily housing that was actually slated for demolition, and there was nobody living there. So we had the opportunity to come in and just do whatever we needed to for our research project. So it actually wasn't a problem in this particular case to tear open the carpet. Okay, so what are the mitigation options? Well, fortunately, it's actually relatively easy and not that expensive to mitigate for vapor intrusion. The mitigation systems are almost identical to radon mitigation systems. Is anyone from part of the country where you know about radon or have come from back east, Appalachia, upper Midwest? Radon tends to be a bigger issue there. And so a radon mitigation system typically is a subslab depressurization system. So you simply suck the vapors out from underneath the slab and you vent them above the roof line. And so these systems are very common in places where radon is a bigger problem. EPA always recommends that everybody should have their house analyzed for radon because you really don't know. California is what we call a zone 2. Nationwide, the nation is split up into 3 different zones for radon. And so California mostly is considered sort of mid-risk for radon. But if you haven't tested your house for radon, you should do it. It's a pretty cheap test, $10 or so. It's probably a little bit more than that now. But it's actually a very inexpensive test. And it's good to know because if you do have a radon problem, it's really pretty inexpensive to remediate it. These kinds of remediation systems, these subslab depressurization systems, run around $1,500, $2,000. They're not horrifically expensive. So there's, subslab depressurization system, and hopefully our graphics will work. Woo! Yeah, very high tech. Ooh. Okay, turn it over to Alana. Here you go.
So if we do have some time after some questions and discussion, we do have a short video that talks about the research that both Kathy and I did on assessing some of this. So it's a 5-minute video. So if we have time, we'll show that. But I just kind of want to recap before we open up for questions. Again, at these legacy hazardous waste sites we have, particularly in Silicon Valley with TC and PCE, it's just been very persistent in the groundwater, and it's just very difficult to clean up. We've been using pump and treat and that type of technology for a number of years, over 20 years at a number of these sites. And we're looking at these alternative technologies that Kathy has presented, and they do show promise. They show one of the difficulties, though, is the concept of matrix diffusion is the fact that it's, as Kathy mentioned, while it was so easy to contaminate our groundwater, it's just very difficult to kind of remove and extract and treat the contamination now that it's in there, particularly in these type formations. And so still likely it will take decades for us to clean up these sites. We have some very large sites. We have had success in some of our smaller sites, and we are hoping to close out for some of those sites. And then finally, the evaluation and science of the vapor intrusion pathway is evolving. EPA and a number of the states, including the state of California, has come out with vapor intrusion guidance, to help in the assessment and mitigation of vapor intrusion. But again, there's ongoing research on it to improve our tools. We get new information about the toxicity of some of the chemicals, such as TC and PC, that makes things a little more problematic sometimes. So that's something that you'll probably continue to hear about. We're continuing our assessment here in Silicon Valley, partnering with the state of California in a lot of that work. And of course, our main goal is always just the protection of human health, and so that's what we're trying to do.